Hello, I want to greet you all, everyone who's watching this video. Today, I've taken this time to talk to you and to share with you the lesson that I just had in theoretical mechanics. It was my first lesson this semester, and it's about dynamics. So I'm not going to take much of your time. Let's get to the major points. So generally, dynamics it's a department of mechanics whereby we investigate motion of bodies and the force influencing that motion. So generally, to understand this concept of dynamics, we have major words in this definition, or which are one, force, and two, bodies. And I guess that motion is something that is not hard to understand. But let's start discussing about force. And when you think of force, what comes to your mind? Okay, force can best be described as interaction of bodies. So the measure of interaction of bodies between themselves is called force. And force is a vector quantity. And what we mean with a vector quantity, we mean that force includes direction and magnitude. But also, when we talk of force, it's important to understand the point of application. It's a vector, and we need to remember that a vector constitutes of direction and magnitude. But when we talk of force, it is also important to talk of point of its application. And when we talk of a body is an object which observes the principles of inertia. And what do we mean when we talk the word inertia? What we mean is it's just the principle describe the fact that if you have a body, and if a body and a force is applied to a body, the body will change its velocity over an interval of time, so that it just don't change its velocity at once, and depending on the size and you know what I mean. If a same force is applied to a very big car, and the same force is applied to a motorcycle, the changes in velocities are going to be proportional to their masses. So when we talk of the measure of inertia, that's now mass. Mass describes the inertia of a body. So having discussed that about the object, and a little bit about force, what kind of forces do we have, the types of force that we have. Actually, we have constant force, and I'll explain what is constant force. Constant force is when we have the magnitude of the force doesn't change, and where we have the direction of the force doesn't change, and at the same time the point of application doesn't change. So we have if these three conditions are fulfilled, then we have what we call a constant force. Then there's another type of force which is called active force. This one now is responsible for motion, for movement. It's what is called active force. Then there's another third type of force is called reactional force. This reactional force is always opposed to motion. Okay, so actually that's what we need to understand basically about dynamics. So with me here I have this, it's about 3.5 pages. Actually our lesson was very long, but I tried to put all the points, the main points which we are going to discuss. They're only going to cover about 3.5 pages. I'll be illustrating some of the equations and some of the drawings for you to understand better what's going on here. So we talk of objects, okay, then we talk of mass, and in some cases we use maybe in other calculations we use what we call a point mass. Now what is in a point mass? A point mass is when we exchange the mass of a body. For example, an object that weighs 10 tons, we just replace it by a point. So a point, so we call this point a point mass, and it's just a model. And to understand it, I can explain it in this way. A point mass is a model of mass which does not have height, which does not have length, which does not have width. So it's just infinitely small. It's like it's there or it's not, but we know that it's there, so that's one. So I want to talk about conditions when we can be able to use this principle of point mass. Okay, so whenever we have an object that is moving but it doesn't have a rotational velocity, it moves with one orientation, it doesn't rotate. So if we have if we don't have rotational velocity, and the other case that we can use point mass is when we have a big difference in value between the size of an object and the distance covered by the object. I will give an example. Let's consider a plane flying from Moscow to New York. So it's approximately 10,000 kilometers, maybe more, maybe less, a little bit. But now if we compare 10,000 kilometers and the size of an aeroplane, it's about maybe 50 to 60 meters. Yeah. So even though a plane would have some movement, some rotational movement, but the fact that it's moving a very long distance, we can consider it to be a point mass. And the other condition or the other case that we can use point mass is when we have a translational motion. Now, a translational motion, I'll give an example. If I move this pen, right, and always it stays vertical, This is called a translational motion. Everything always corresponds to the same position from the center. So when we have a translational motion, we can consider that case as a point mass. So in dynamics, there are three laws, and these laws are called Newton's laws. And it happened so that Newton lived around in about 1600 and 1600 years, like 1680. That's when like in the 80s, 1680s, that's when he formulated his laws. And he just didn't get them from Norway. He used the experience of the humanity, how people have studied motion, and he came up with three laws. And there are also laws that we use in dynamics. So the first law goes by this. It's called the law of inertia. So what it basically states is that if a body is not acted upon by an external force, it will remain in a state of rest, or it will remain in motion with a constant velocity. Only until when another force acts on that body will it stop. So if we have a body moving, and if there is no other external force acting upon it, it will move with a constant velocity. It will move with a constant velocity, and it won't stop. Here there's another interesting point that I want to discuss with you. Before Newton, so about 40 years before Newton, Galileo proved that a body can move not because of force, but it can move because of its inertia. I'm going to illustrate what he showed to people. So given an inclined surface, and to place an object on an inclined surface. So due to the pull of gravity, the object moves down the plane and it reaches the horizontal plane. Now at the horizontal plane, the pull of gravity is equal to the normal reaction, but the body continues to move. And Galileo shows that the body continues to move because of its inertia. So this is also another interesting part about motion. Okay, that was all about the first law of motion. That was by Newton. He formulated it 1687 in that year, that is 1687. Let's move on forward to law number 2, the second law of motion, which is the basic law of motion. In theoretical mechanics, we define it as the product of mass of an object and its acceleration, which is caused by a force, is equal to that force. And at the same time, we need to remember that the direction of the acceleration is always the same as the direction of the force causing that acceleration. So here is how we illustrate it so here's the illustration. Theoretical mechanics. Mass represented by a letter M, multiplied by acceleration, and report our vector sign. This dash is equal to a 4, and this dash just implicates that it's these are vectors. Acceleration is a vector and force is a vector quantity. But in physics, they will have it in this way. Force is equal to mass multiplied by acceleration. So if you write in this way in theoretical mechanics, they will tell you it's wrong if you start by writing force is equal to mass multiplied by acceleration. And if you do the other way around, if you write mass multiplied by acceleration is equal to force in physics, they will consider you wrong. But between these two equations, nothing is different. Nothing is different. But this is the way the modern scientists have decided to write this law. But this is not how Newton formulated it. According to Newton, he wrote, acceleration of a body is directly proportional to the force being applied to that body and inversely proportional to the mass of that body. So in this three way of representing this law, so we can call it law 2. So in this way of representing this law, there are three ways. So you could choose any one that you feel comfortable with. Okay, now let's quickly talk about the third law of motion, and it was formulated by Newton too. And this law states that for every active force there is always an equal reaction force to that force that is acting on another body. There's always a reaction of force which is equal in magnitude to the active force, but it's opposite in the direction, and these forces act in the same line of in a straight line. They're always in a straight line, the action and the reaction forces. So I think this is what we have on the third law of motion. So we are done with these laws, but maybe to illustrate the third law of motion and use the illustration. So given a body, and we have one point, let's just name this point a point 1, and another point on the body, point 2, And let us imagine that we have a force pulling from 2. This is called F12. And if this point is fixed, point 1 is fixed, we will always have an opposite force which is equal to F21. And these forces, F21 is equal to F12. And if you look at this direction, the direction of the forces, it's different, but they are equal in magnitude. This is all we need to know about the third law of motion. Okay, now it's important for us to discuss the SI units. These are international standard units that we use in dynamics. So in dynamics, the first symbol that we have, it's L. It represents length. And the SI unit of length, it's meter. We just represent it with a small letter M, and this is meter, 1 meter. And the second important symbol is T, which is time, and we represent it with a small letter S, which is the unit, which is the second. And the other symbol that we have, it's big letter M, that is mass, which is measured in kilograms. So these are the units. So one Newton, it's okay, let me say a Newton is the measure of force, and 1 Newton now, it's written in this way: big letter N. Big letter N. I'm sorry for that H. It's because in another language an H is an N. Okay. So 1 Newton, and a Newton is equal to 1 kilogram meter per second squared. So a Newton is the amount of force which is required to change the acceleration of a 1 kilogram by 1 meters per second. So that's all about the SI units of the measurements that we are concerned in dynamics. Okay, now let's talk about major kinds of force, major kinds of forces. So the first force that we're going to talk about, it's gravity, the force of gravity. Okay, and this is how we can illustrate a force of gravity. If we have an object and we have a center of gravity on the object, and that's where this force acts, and it's always pointed to the surface of the earth, and it is always perpendicular to the surface of the earth. So in theoretical mechanics, we represent this force by P, and it's a vector, because it constitutes of direction and magnitude, and this force is equal to from the second law of motion, we know that force is equal to mass multiplied by acceleration, but here we have the gravitational acceleration, which is represented by the letter G, and this G has been calculated to be approximately 9.81 meters per second squared. And if we write this in this way and remove the vector form, the vector sign, that dash on top of P, it now represents P is equals to mg, and this is no longer force of gravity, it's now weight of the object. Now represents weight. So this is only what we can talk about the force of gravity. Then the second force that we might want to take a look on it, it's the gravitational force. Gravitational force, it was also formulated by Newton, Isaac Newton. This is a force that exists between every masses. So what it actually means that if we have two objects of different masses, the other object 1, object 2, the object 1 attracts object 2, and object 2 attracts object 1, and this force is equal. So this is the way to illustrate it. So if we have one object and the second object, and if we know the distance between these objects, let's give us distance a sign r, and for this force we need to understand we have a constant which is called G. G is the gravitational constant, which is equal to 6.673 multiplied by 10 to the power negative 11. And then if this is known, and here we have m1 and we have m2, these are our masses. So the forces of attraction, this is the direction of the forces, and this force is equal between the two objects, and the force is given by this formula: G multiplied by m1 multiplied by m2, or divided by r squared. This is the formula that we have. This is now another kind of force which is called gravitational force. Then another kind of force that we have is called frictional force. A frictional force is this force that happens when you try to move a body that is on another surface, and it's the resistance that you get, and it is proportional to the normal reaction on the surfaces, and what we call the coefficient of friction. So here basically, if we have an object and if we have a surface and we have the force of motion going in this direction, the force of friction is always acting in the opposite direction, and if we have the weight acting in this direction, that should be weight. We always have a normal reaction acting upward. So given So given coefficient of friction to be lambda, frictional force would be equal to lambda multiplied by the normal reaction of the body. So this is another kind of force. And then finally we would want to look at the last force that we can talk of today, and that will be the elastic force. So generally the elastic force is the force that happens when someone tries to stretch a spring or another elastic material. So this force is always directed in the direction which restores the original length of the spring, and we can easily illustrate that. Given that we have a spring and this spring is length LO. This is the original length of the spring. Then we stretch it. With other distance, let's say delta x. So in this case, the force at B will be pointed in the opposite direction of increase of delta x, and if we know the spring constant, let's give it the letter C. This would be our spring constant. Our spring constant. So the force of elastic in this case acting at the point B would be equal to force at B, which is equal to spring constant multiplied by delta x. So how do we define a spring constant? Spring constant is the amount of force that is required to stretch that spring by 1 meter. So it's defined as Newton per meter. So thank you guys for watching up to this time. If you watched until the end, it means you're interested in mechanics, you're interested in knowing more about engineering, you're interested in knowing more about science and technology. And I want to tell you this, I'll be back with theoretical mechanics next week, Monday. And I'll be saying what I would have learned by that time, and if we go together, you'll be also a master in theoretical mechanics. But of course, I have a very interesting timetable, and every day I'll be having different subjects like further mathematics. I'll be having programming, I'll be having computer graphics, engineering, computer graphics, and I'm willing to share with all these things with you. And if you're interested in knowing what's happening in this engineering world and if you have a dream to become an engineer, and if you have sons or children which dream to become engineers, just inform them about this, and they will know what it takes to become an engineer. It's going to be more interesting, more, because I'll be solving some mathematical problems. I'll be drawing in 3D modeling and something like that, programming, everything. It will be on this channel. This was just about mechanics and dynamics. So see you next Monday. Again, if you like mechanics, just hit a like and don't forget to subscribe, and inform everyone who is interested in knowing more about engineering, science and technology. See you next time. Stay tuned.